Imagine I offered you the chance to buy an investment for $100 with a guaranteed average return of 10% every single period. There's just one catch. Each period, its value can move in one of two ways. Heads, your investment rises by 60%. Tails, it falls by 40%. Both are equally likely, and you can stay invested for as long as you want. Would you invest? To me, it sounds like an absolute no-brainer, and in fact, in 1738, mathematician Daniel Bernoulli wrote about a related coin game paradox. Hidden inside it was an idea with ramifications for every single investor on the planet, and most people have no idea it exists. So let's indulge Bernoulli and play out his game. We can use a coin because there are only two outcomes of equal probability. Heads, remember, increases your wealth by 60%, and tails decreases it by 40%. Let's flip it 100 times. Here's one random series of flips that I've generated. In this instance, we end up with just $13. Sounds super unlucky, right? What are the odds? I'm going to transform this chart to a log scale so the range of outcomes is a little clearer. Now, let's play the investment game another 999 times and see where the mean, or arithmetic average, final wealth ends up. A whopping $1.4 million after 100 flips of the coin. In the language of probability, this value is the expected value, or expectation, and as you probably already know, it's calculated by adding up all the final wealth values and dividing by the number of investors who took part. We do not actually need to find 1,000 investors willing to part with their money to discover the expected value. We can calculate it instead. A 1/2 chance of landing heads, which increases your wealth by 60%, has an expected contribution of plus 30%. A 1/2 chance of landing tails, which decreases your wealth by 40%, has an expected contribution of minus 20%. Add those two numbers together and each flip is worth a gain of 10%. Transform that 10% gain into a decimal and wealth gets multiplied, on average, by 1.1 on each flip. Do that 100 times and we get to $1.4 million. So I'm going to ask you again, would you still play the game? Before you answer, there is one thing that $1.4 million figure is hiding. It's just one number summarising a huge distribution of possible outcomes. So let's look inside it. This is the luckiest path in our sample. After 100 flips, the luckiest investor finishes with $226 million. Here's the second luckiest, $31.8 million. These are not just slightly better outcomes, they are extreme outliers. So what does a more typical player in our investment game experience? This is the middle path. Half of all paths finished above it and half finished below it. Starting with $100, the typical player finishes with just $13. Half of players lose at least $87, and 2 out of every 3 players finish below where they started. Here's break even. Everything below this line has made the player poorer. And at the far end of this distribution is the unluckiest path. After 100 flips, it has been reduced to virtually nothing, 0. So we have a very strange result. The expected wealth is $1.4 million. The typical player ends with just $13. Both are true, but they answer completely different questions. The expected value asks, if I could run this game across many parallel worlds, what would the average final wealth be? And for that reason, we call it the ensemble average. It's the average across an ensemble of possible paths. But you don't get to live in an ensemble, you get one sequence of outcomes through time. Now that distinction matters because the ensemble average is being held up by a handful of extraordinary winners. Only around 1% of paths finish above the expected value. So watch what happens when we remove the most exceptional paths. The average collapses. Remove just a handful of dominant winners and $1.4 million becomes roughly $228,000. Still a large number, but dramatically different. A handful of paths clearly dominated the average. And that's why expected wealth can be a misleading phrase. It sounds like something you should expect to experience. But for one person playing this game through time, it's not. Let's return to the middle path. Earlier we saw that the typical investor lost money. But was that foreseeable? And could that investor have worked out before flipping a single coin that the middle outcome, or the typical outcome, would be unprofitable? To answer that, we need a different average, the time average. It asks what happens to one player who repeats the game over time. If you watched my previous video, this is mathematically the same as the geometric average. I'm calling it the time average here because it makes the intuition clearer. It describes the wealth path one investor actually experiences as gains and losses compound through time. A gain of 60% means your wealth is multiplied by 1.6. A loss of 40% means your wealth is multiplied by 0.6. The geometric average gives us the growth factor of those two numbers. 1.6 multiplied by 0.6, then square rooted, gives roughly 0.98. That means each flip multiplies your wealth by 0.98, or expressed as a return, minus 2% per flip. Start with $100 and compound that loss through time. After 100 flips, you end up at around $13. That is the time average. It does not tell us the exact sequence you will experience, but it tells us the compound growth rate faced by a player who has to live through one sequence of outcomes. And hopefully now you can see the central problem. The ensemble average explodes towards $1.4 million, while the time average collapses towards 13. They're not equal, and they're not even close to equal. And here's where I'm going to introduce the concept of ergodicity. This toy investment game that I've set up here is said to be non-ergodic, because the average across many possible worlds does not describe what happens to one person living through time in one world. To see the contrast, let's change the game. This time, heads gives you a flat $60 rather than increasing your wealth by 60%. Tails costs you $40 rather than incurring a 40% loss. The coin is still fair, but now the changes are additive rather than multiplicative. A 1/2 chance of gaining $60 contributes plus $30. A 1/2 chance of losing $40 contributes minus $20. Together, that is plus $10 per flip. And because the gains and losses no longer scale with the wealth that you have left, the time average and ensemble average now agree. This is now an ergodic system. In this additive game, most players actually win, whereas in the first multiplicative game, even when the arithmetic average was positive, most players lost. That's the distinction. One world is additive, plus $10 per flip, when most players won. The other is multiplicative, plus 10% per flip, where most players lost. Okay, so you're probably thinking, this is a lovely thought experiment, but where's the relevance to real investing? And that's a natural question to ask, because we're often shown one historical path and invited to treat it as the whole story. And unfortunately for us, investing really does live in the non-ergodic world, as we're about to see. This is the S&P 500 since 1950. You may look at a chart like this and think, this is just what investing does. Let's transform it to a log scale to see it a little more clearly. Now, have you ever considered that the market did not have to deliver its good and bad periods in precisely this order? What if the same historical ingredients had arrived in a different sequence? To explore that, we can create alternative histories using real S&P 500 returns, a bit like shuffling a deck of cards. I'll put the exact method in the description below. We're effectively taking stretches of real market history and randomizing their sequence to create thousands of plausible histories assembled from the same material. And because investing compounds, changing the order can change the outcome dramatically. These are not predictions, nor are they claims that the future will literally replay the past in shuffled order, but they are stress tests for sequence. They're a way of asking how much of the outcome came from returns themselves and how much came from the particular order in which they arrived. Some plausible paths finish far above the history we lived through, and some finish far below it. The 95th percentile is a very favourable but still plausible version of history, while the 5th percentile is an incredibly unfavourable one. It's worth noting though that each of those two paths was as equally likely to have happened. Let that sink in. The ensemble average asks a strange question. If I could invest across thousands of parallel histories, where would I end up on average? But no investor gets to live thousands of histories. We only get one, and that's why I believe time average matters. It asks, What kind of compound growth would I expect to experience if I had to live through one sequence of returns? And then there's the actual S&P 500 history, the path investors really got. What this shows is uncomfortable. The S&P history we know was not just normal, it was lucky. Not the luckiest path, not the best possible path, but meaningfully better than the typical single path in this universe of parallel worlds. So these three lines answer three different questions. The white line asks, what happened to my investment in the one world I got to experience? The yellow line asks, if I could invest for 1,000 lifetimes, where would I end up on average? And the purple line asks, where would I expect to end up as the typical investor? None of these is the universally correct answer. The danger is treating the historical chart as though it were a promise. It's one realised route through a much wider range of possible routes. But that doesn't mean investing is hopeless. It means risk is more than the volatility we can see on one particular chart. And it means we can make better decisions once we stop confusing a good average with a good path. In the next videos, we'll use this idea properly, not to give up on reward, but to explore how we can reduce the risk of paths that do the most damage.